Hello, my name is PhlipJonathan from Lancaster University in Shell, and today I'd like to talk to you about return values subject to uncertainty. This is joint work with my colleagues John Thorne and Jenny Wadsworth at Lancaster and David Randall at Shell. So there are two relevant papers here for the work. The first is about return values subject to uncertainty, and the second is discussion of a more decision theoretic approach to design calculations. So a quick overview of the talk. First we'll consider some return value basics, and then discuss the problem at hand today, right, which is the incorporation of epistemic uncertainty in return value estimates. So we'll consider some possible estimators, show that these estimators have theoretical orderings, and then look at the results of a simulation study. Finally, I'll end with some conclusions and maybe suggest a better way than return values. Okay, so what is a return value? So if I think that I've got a random variable a that represents the maximum value of some physical quantity x per annum, so then what I'm interested in is the annual return value xn, can be defined, which can be defined using this expression. So essentially what I want to be able to do is I want to be able to find a high quantile of the distribution of the annual maximum. And typically when people are looking at return values, then they typically think about between maybe 100 and 10 million or 100 million years. So there's an alternative definition which is done in terms of the distribution of the annual maximum, an, and it follows from the asymptotic limit of 1 minus 1 over n to the exponential. So then you can use the distribution of the annual maximum in place of the distribution of the annual maximum, right? But you're looking then at a different quantile. Okay, so in estimating the return value, we need to have some knowledge about the distribution function fa of the annual maximum or of the annual maximum. So we could try to estimate fa using extreme value analysis and a sample of independent observations of annual maxima, but this is a bit inefficient. It better would be to try to estimate the distributions of peaks of a threshold, for example, of the original x, and then from that infer the distribution of the annual maximum and hence the return value. And how do we do this? Well, we do this using the standard extreme value theory. For peaks of a threshold, we use the generalized Pareto distribution, which is shown here. We can calculate the full distribution of the underlying variable x, and once we've estimated the tail, and we can calculate the distribution of the annual maximum like this. So this involves again the distribution that we get via the extreme value analysis, and this is some rate of occurrence distribution, which is typically maybe a Poisson. So what's the problem with all of this? Well, xn, so the return value, can be estimated easily in the absence of uncertainty, but in reality the parameters that we need, so the rate of occurrence of storms lambda, the threshold psi, the scale sigma, and the shape of the generalized Pareto tail psi from a sample, and these samples are not, these values are not known precisely, so they're only known with error. So this is known as epistemic uncertainty, and this obviously is going to affect the estimates of return values that we make. So there are a number of plausible different estimators for return values under uncertainty, but the issue is that these different estimators perform differently, so they give different bias and different variance. So the question then is, which estimators are likely to perform best in fairly general circumstances? And maybe an even more fundamental question, is it sensible or even desirable to estimate return values at all? So two generic mathematical rules, if you like, for incorporating uncertainty. So the first one is when I have a conditional distribution f of y given z of random variable y and random variables z as well. So this is multivariate here, and if I have the joint density f of z of all the z's, then I can go from the conditional distribution to the unconditional predictive distribution f tilde of y using this expression. So it's easy enough. Essentially all I'm doing is integrating out over the zeta here using the joint density. So this gives me a predictive distribution. So this is quite an important concept in terms of estimating return values. The other approach is when I have a deterministic function g of the parameter z, then I can still integrate out over zeta. Now I get an expectation of this function z in a similar fashion. So here z and zeta are going to be my set of parameters that I'm interested in, and y would be the annual maximum or the n-year maximum. Okay, so now then there are 4 different return values that I would like to consider today. The first one is motivated by the widespread approach of just ignoring uncertainty in the parameters zeta for the estimation of return values. So essentially then what I get is I just estimate the mean of the uncertain parameters and I plug that into the equation for the return value, and that gives me a return value estimate. Okay, that's simple enough, right? So there's a related estimator converging with increasing ed based on the n-year maximum, and there are similar or analogous choices of estimator based on, let's say, the mode of z, or the median of z, or a particular quantile of z. So another example is where we are going to calculate the return value independently for each value of zeta or z that we have, and then at the very end take expectations over all of the different estimates for the return value that we had. So we're going to call this xn2. Okay, so essentially what we're doing is solving for the quantile xn of zeta of the distribution of A with non-exceedance probability 1 minus 1 over n for a large number of parameter choices zeta, and then we just take the mean. So again, there's a similar definition that you can use using the n-year maximum distribution. So the third definition is a little bit different, and here what we're doing is going to first calculate the predictive annual maximum distribution. So again, this is using the expression I showed a couple of slides ago. Now what we're doing is integrating out over the parameter uncertainty the distribution of the annual maximum conditional on uncertain parameters. So then this gives us the predictive distribution, and then what I'm going to do is to find the 1 minus 1 over n quantile of that distribution as is given here. So briefly what we can do, we can call this estimator q tilde a. So q is kind of like a quantile or inverse function corresponding to the predictive distribution of the annual maximum. So this is kind of like the obvious go-to estimate for Bayesian analysis. Okay, then the fourth estimator that we have is kind of like the third one, but now what we're going to do is base the predictive distribution on the distribution of the n-year maximum. So again, exactly the same procedure, but now we're basing it on an, whereas in the previous case we based it on a. Now, of course, instead of finding 1 minus 1 over n quantile, we have to find the x to the minus 1 quantile of this distribution, as I showed at the start of the talk. And then we can write this estimator briefly as q tilde of an of x to the minus 1. And again, q is this quantile function. So, just to summarize, we can take averages over uncertain parameters and plug in the average into the return value calculation. We'll call this Q1 from now on. Or we can calculate the return value for all sets of estimates independently and then take the average, and we're going to call that Q2. The third way is that we're going to calculate the predictive or the average annual maximum distribution and then take the 1 minus 1 over n quantile. And the fourth way is that we're going to take the average n-year maximum distribution and then take its x to the minus 1 quantile. So these are the 4 estimates, and I'm going to refer to these in what's coming as Q1, Q2, Q3, Q4. It's important to note that without parameter uncertainty, these estimators are equivalent. But with parameter uncertainties, their estimators are different. So first of all, I'm not going to label this slide. I want to show you that theoretically we can show in fairly common cases that these estimators are going to be ordered. So some values are going to be bigger than others. And clearly that's not a very desirable property. And in particular, we can show that some of the estimates are always going to, or at least in these cases, are going to show bias with respect to the true value, which is noted by Q0 here. So we already know just from theoretical consideration that these estimators are going to give us different estimates of return values. We can illustrate this further using simulation study. What I've done here is I've taken data from a generalized Pareto distribution for a range of different values of psi naught, the true shape parameter, and with a fixed scale parameter of 1. I've taken different sample sizes, and I've assumed that there are 100 events per annum. And then what I've done is looked at the estimation of return values for different return periods, 100 and 10,000 years. And I've repeated this whole thing 100,000 times in order to make sure that I've reduced my my uncertainty. So then I'm going to quantify the quality, if you like, of the return values that I get in terms of the fractional bias of the return value, in terms of the fractional bias of the exceedance probability associated with the return value, and then in terms of the fractional bias of the log exceedance probability associated with the return value. The last one is important because typically when we're working at likelihoods and things like that, we're actually multiplying probabilities together. So that means we're adding together things on a log scale. So having good performance in terms of log bias is very important as well. Okay, so these are the results. So in this case, I'm looking at a sample size 100 or 1 year, if you like, a sample size of 1,000 or 10 years. And here I'm looking at a 1,000 sample of size 10,000 or 100 years. And what I'm trying to do is to estimate the 100-year return value. And what I have is 4 different estimators. And you can see here that this is the 0 line. So this is would be the perfect estimator giving 0 bias. So you can see that the 4 estimators, none of them are giving excellent performance, but the one with the best performance is this estimator Q2. So that's the estimator that takes the expectation over essentially independent estimates of the return value. So this is the plug-in estimator, the black line, which is just taking the expected value of the parameters and plugging that into the return value calculation. So this dotted line here is what we would prefer from a Bayesian perspective. This is the predictive, this is the estimate based on the predictive distribution at the annual maximum. And you can see that it's really biased high. So it's overestimating the return value for this sample size by a dramatic amount, by up to 20%. As the sample size increases, then the pattern in the bias is repeated essentially, but the extent of the bias is much smaller. So here you've got a range of maybe up to maybe plus or minus 4%. Here you've got a range of, well, much less than the 1% here with much larger samples. So this ordering of the return value estimate is entirely consistent with what we have proven already theoretically. And we might conclude that this Q2 estimate is the best of the lot. If we now look in terms of the bias in the exceedance probability, we have a relatively similar story. You can see that the Q3 estimate is underestimating the exceedance probability, and all the other estimates tend to overestimate the exceedance probability, with the exception again of this Q2 estimate, which gets pretty close to unbiased for larger values of the underlying shape parameter. The pattern changes a little bit with increasing sample size, but not to a great extent. The third case is where we're looking at the fractional bias in the log exceedance probability. And here you can see that the Q3 estimate, the predictive estimate based on the annual distribution, is terrible, essentially with giving a massive bias, which I can't even calculate for smaller values of the psi naught parameter. Again, you can see that the Q2 estimate seems to be giving the best performance in terms of being near to 0 bias. Okay, so what have we found after all of this? Well, The first thing is that there are different estimators, and the different estimators give different estimates, and they give in particular systematic bias. So why is this happening? Well, essentially, it's down to a very simple mathematical fact, right? And that's that the expectation of a function is not the same as the function of the expectation in general, and that's why these problems are happening. So the bias effects we're seeing are small for small sample sizes, and they go to 0 as the sample size goes to infinity, which is of course comforting. Of all the estimators that we looked at, the expectation over these independent estimates of the return value seems to be the least biased, and this can be estimated from the distribution of the annual maximum or from the distribution of the n-year maximum. The obvious statistical go-to estimate, which is the one based on the predictive distribution of the annual maximum, is giving poorer performance. So from this, we kind of conclude intuitively that it's better to be taking averages over estimates at the end of the calculation, and to avoid summarizing distributions, if at all possible, until the very, very end of any calculation that we want to make. And this is obviously points us in the direction of a decision theoretic approach to structural design. So some caveats here. The work that I've shown you so far is based on maximum likelihood estimation, but in the paper we've discussed other inference schemes as well. And obviously there are lots of other estimators of return values apart from the 4 that I've discussed here today. We've discussed the bias in the return value estimates, but obviously there are uncertainties, variances if you like, in those return value estimates as well. And they can be quite large relative to the bias in some cases. So that's important to take into account. Another question perhaps is regarding how we should do this analysis is whether safety factors elsewhere in the design process require us to calculate design values of following a particular procedure, and because that procedure was used when the safety factors were set in the first place, for example. And then maybe most importantly, when practitioners are discussing differences in return values, those differences only really make sense when the return values themselves have been calculated using the same approach. And our impression is that often discussions of difference in return values are based on different calculation schemes, and therefore it can't be expected that the return values are comparable. So to end, I'd like to point to a different way of doing things, an approach we think is better, and this is based on decision theory. So I'll just show you an example of how this might work. So we might consider structural loading R over some period for structural strength R0. Okay, so then what we're going to do is to define a loss function. So the loss function essentially says that the structure will fail when R exceeds R0, and otherwise that the structure will be okay. So then what we're going to do is to estimate a conditional distribution here for uncertain environmental parameters, and this is hard work because this might involve sophisticated modeling of the environment and also of the wave structure interaction, for example. So this is computationally challenging. But once we've done this, what we can then do is calculate the expected loss, and this is the expression for the expected loss. So this then can be adjusted. We can adjust the expected loss, and by changing the structural designs, changing the structural strength, so that the expected loss is acceptably small. For example, the failure rate of 10 to the minus 4 per annum, for example. So using this approach, we propagate uncertainty in full through the design calculation, and then we integrate over uncertain parameters at the very end, and this is exactly like that Q2 definition of the return value that we mentioned earlier. And importantly, this approach makes no use of return values at all. So return values are not needed at all in this approach. Okay, so I've come to the end of the talk. These are the two papers that I referred to, and thank you very much for listening, and hopefully I can take some questions now. Thank you.